Hi, my name is Dustin Stansbury, and today I'm going to be telling you about a study that I conducted with Thomas Nasolaris and Jack Gallant here at UC Berkeley. When we explore the world around us, we tend to visually categorize the scenes that we see with specific categories like the beach, or an office, or the mall. Scene categorization is generally based on the objects that we observe in the scene. For example, if you see sand, water, and sunbathers, you'll probably categorize the scene as a beach. And if I say the word beach, you'll likely recall these objects plus many other related objects like palm trees, sandcastles, volleyballs, and so on. These recalled objects are very different from those that would come to mind if I were to say another word like office. These observations suggest that over the course of your life, you learn which objects tend to co-occur in natural scenes. And if this information is represented in your brain, you likely use it to make perception more efficient in daily life. We decided to investigate whether or not the intrinsic categorical structure of natural scenes is indeed represented in the human brain. To do so, we used a two-stage process. First, we used statistical learning methods to find the intrinsic categorical structure of natural scenes. Then, we measured human brain activity while viewing natural scenes and compared this to the intrinsic categorical structure of those scenes. To recover the intrinsic categorical structure of natural scenes, we first labeled all the visible objects in a library of over 4,000 natural scene images. We then used a statistical learning algorithm to analyze these labels. This particular algorithm was developed originally to recover the underlying topics in large collections of text. Thus, when applied to the object labels, the algorithm learns which objects tend to group together in the images. These groups correspond to scene categories. Each identified category is defined as a set of probabilities over all the objects in the labeled images. Each probability gives the likelihood that the corresponding object occurs in a scene belonging to that category. Here we show a few examples of the categories identified by the algorithm. Each category is represented as a list of objects that are most likely to occur in the scene belonging to that category. Darker labels indicate objects that are relatively more likely to occur. Now keep in mind that these categories are learned from the image labels alone. We gave the algorithm no information regarding the type of categories it should learn. Even still, the categories identified are intuitive natural scene categories. For example, the category on the far left consists of scenes that are likely to include a table, a sofa, a wall, a floor, decoration, and a window. Thus, this category is intuitively interpreted as a living room scene. Inspection of the other scene categories indicates that they too correspond to real scenes that we would find in daily life. After identifying these natural scene categories, we wanted to determine whether, and if so, how, these categories are actually represented in the brain. We placed 4 human subjects in an MRI machine and recorded their brain activity while they viewed over 1,000 natural scene photographs. Functional MRI measures blood flow caused by neural activity. The blood flow is sampled from tiny cubical volumes of the brain called voxels. Our voxels were roughly 3 millimeters on each side, and we recorded from approximately 20,000 of these voxels in the visual cortex of each of our subjects. In order to relate the recorded brain activity to the learned scene categories, we had to devise a way of objectively describing each of the viewed scenes in terms of these categories. We did this using a statistical technique called Bayesian inference. Using Bayesian inference, we calculate the probability that a new scene belongs to each of the identified categories based on the objects in the scene. For example, this scene of a grilled fish dinner would be assigned a high probability of belonging to the dining category because it contains a table, a plate, and drinking glass. It would also be assigned a high probability of belonging to the aquatic category because it contains a fish. However, it would be assigned a low probability of belonging to the other remaining categories. Now, after scanning the subjects, we labeled each of the objects in each of the viewed scenes. We then used these labels to infer the probability that each of the objects belong to each of the learned scene categories. Then, using regularized regression analysis, we modeled the relationship between the evoked activity and the learned scene categories. What results is a model that characterizes how each voxel responds to each of the learned scene categories. We then wanted to determine how accurate each of these models were in different parts of the brain. To do so, we recorded a high-resolution anatomical scan of each subject's brain. We then used this data to create a 3-dimensional model of the cortical surface of each subject. We then flattened this surface so that we could see the entire cortical sheet at one time. Here we zoom into the back of the brain, where the visual system is located. The left hemisphere of the brain is on the left, and the right hemisphere of the brain is on the right. We can then color each voxel location on the cortical sheet according to the accuracy of the corresponding voxel model. Bright yellow voxels indicate areas where the models are most accurate. We found that voxels located throughout anterior visual cortex were accurately modeled this way. This makes sense because previous studies have shown that anterior visual cortex is involved in many different aspects of visual perception, such as scene processing and face perception. One nice application of this approach is that we can use the same modeling framework to decode brain activity. Essentially, what we do is we use the same raw data, but run the regression analysis in the opposite direction, trying to predict scene categories from evoked brain activity. What results is a decoder that can predict the scene category of a novel scene from the activity evoked by that scene. Here we show a few examples of the decoder. On the left is a scene that was viewed by one subject. The most likely scene categories decoded from the brain activity are shown on the right. Here, saturation of each label indicates the decoded probability that the viewed scene belongs to the corresponding category. The decoder indicates that the viewed scene was a member of the urban or boatway categories. This is an accurate description of the scene. Here's a second example, decoded from a second subject. The decoder indicates that the scene is likely a member of the living room category. Now you may recall that the learned scene categories are defined in terms of the probabilities of objects occurring in scenes belonging to those categories. Now using this information, we can extend the decoder in order to predict the likelihood of individual objects occurring in each of the decoded scenes. Here's an example of objects predicted for the urban boatway scene shown earlier. Label saturation indicates the probability that the viewed scene contains each object. For this scene, the decoder predicts that the most likely objects are a building, boat, and so on. These objects either occur in the specific scene or they are consistent with the scene context. We find that we can accurately decode scene categories and individual objects in a diverse range of natural scenes. This is all done from evoked brain activity alone. Pretty cool, huh? Now, if you want to find out more about the study, you can read the full paper in Neuron, or you can check out our website. Thanks for listening.